Hello. In today's first video on radicals, I'm going to introduce what a radical is. I'll go through some of the stability and resonance that you'll see with radicals, and I'll finish off with going through the common patterns of radical mechanisms that you will see. Right, so radicals have an unpaired electron, and radical reactions involve one electron transfers. So for an example, you've got chlorine gas here, Cl2. This can undergo a homolytic cleavage, and homolytic means the bond breaks up with the two electrons. One electron goes to one atom, the other one goes to another atom, and I'll end up with two chlorine radicals. This is a shorthand way of writing it, right? I can fill in all of the lone pairs, but often when you're writing a radical, you'll just indicate that it's a radical with one dot for the electron. Now, something some people misunderstand with radicals is they're always neutrally charged. You don't have a negative or a positive radical. So you just have a radical and it doesn't have a charge. Right? The reasoning here is chlorine has 7 valence electrons, and there's 7 assigned electrons here to give you 0 overall charge. And also notice in this the arrows that I'm using. Right, I used fishhook arrows. They indicate one electron transfer. The common arrows you would usually see used indicate 2 electron transfer. Up to this point, you may have never done radical reactions, and it may take a little bit of time to get used to writing those fishhook arrows, but it's very important so that you're indicating you're only moving 1 electron and not 2 electrons. Now for stability of radicals. It's the same as for carbocations. And like carbocations because of hyperconjugation. Right, carbocations are missing a pair of electrons, making them positively charged. So the hyperconjugation, you donate electron density to that empty orbital, and that stabilizes it. A radical is similar. It's missing an electron. It only has 1 unpaired electron, not 2 electrons like a usual non-bonding pair of electrons would have, so it's still electron deficient, so hyperconjugation will help to stabilize it as well. Now the order of stability, if you don't remember from carbocations, is going to be methyl is less than primary, which is less than secondary, which is less than tertiary. Now you can additionally have resonance stabilization in 2 types of radicals, or in 2 positions of the radicals. If it's allylic or benzylic. So allylic would look something like this. I've got my radical, the resonance here. I would move 1 electron, 1 electron, and 1 electron. So I would end up forming a new pi bond here and breaking the pi bond that had been to the right, and getting a radical there. Now in this resonance, it would be favoring that structure because it's secondary radical versus a primary radical, but there is resonance stabilization. So this radical here would be more stable than if I just had that because of the resonance stabilization. And a benzylic, so if I put the benzylic over here, there's a lot of resonance structures the benzylic one could have. So resonance-wise, you would now have that, and you could continue to go throughout the entire ring doing the same resonance stabilization. And I'll let you try that on your own. See if after this first one you can continue drawing the arrows, right? The next one I'd have an arrow move there, an arrow move there, and an arrow move there. Oh, I missed one arrow on this first one, right? We have to have 3 arrows moving with all of our resonance stabilizations with the allylic and the benzylic positions. Okay, so next I want to go through some of the common patterns you'll find in radical reactions. Number 1 is going to be homolytic cleavage. And this requires either heat or light energy. So this is a very common radical reaction in the atmosphere, right? A lot of gases will undergo homolytic cleavage, and that's the example I'm going to give you below. So I have oxygen. Oxygen's often drawn with a double bond, but this structure here is actually closer to the true oxygen structure that you find, right? All you have to do here is draw that to then have the resonance structure that's the more common oxygen that we see, right? But for this homolytic cleavage, what's going to happen is that bond will split, and you will get two oxygens, right? This happens all high up in the upper atmosphere where there's a lot of light energy from the sun. It has the energy to break diatomic oxygen into atomic oxygen. You'll never really see atomic oxygen down at ground level because of how much energy is required to undergo this homolytic bond cleavage. Number 2 is going to be addition to a pi bond. And this actually forms a new sigma bond. So this can be a very useful reaction for organic synthesis when you're trying to make a new sigma bond, because there's not too many mechanisms to be able to do that. So for example, I've got chloride, and I'm going to put in just the one dot to indicate it's the radical version of chlorine. And then I have my hydrocarbon here. I'm going to draw fishhook arrows to empty space here, which is going to be the new sigma bond. And then my other arrow is going to move to the carbon to the right of the pi bond. So now I've formed a new bond, but I have lost a pi bond. So I form a sigma bond, but I lose a pi bond in addition to a pi bond. Number 3 is going to be a hydrogen abstraction. Now this is a critical reaction for breaking down gases in the atmosphere. Some of the most potent greenhouse gases, such as chlorofluorocarbons, CO2, they don't have a hydrogen on them that can be abstracted. And what happens is when the hydrogen is abstracted, it forms a radical. And that radical will continue to undergo reactions until ultimately that compound is broken down. But if you don't have a hydrogen, you're not able to start that whole reaction chain by forming the free radical through hydrogen abstraction. So how this works, I'm going to continue with using atomic chlorine here. And then that is my other compound. Again, here I'm going to be drawing an arrow to empty space. And then my other fishhook arrow there. So I will form HCl. And then I now have a radical in that position. Right, and I chose this molecule because you have a tertiary radical, so that's going to be the most stable of the radicals you could have. Number 4 is going to be very similar, but this one is halogen abstraction. In a halogen abstraction, I have my first compound here, and then diatomic chlorine. So I draw to the empty space again because I'm forming a new sigma bond while I'm breaking another sigma bond. So I end up with radical atomic chlorine and then my new chlorine-carbon bond from the hydrocarbon. And notice with these reactions, I start with a radical and I finish with a radical just on a different compound. Same with halogen abstraction. I start with a radical, I finish with a radical, but it's shifted which compound it's on. If you have two radicals that react with each other, then you can have a product that doesn't have a radical. But if there's only initially one radical in your reactants, your products, one of them is going to have a radical. All right, number 5. This is going to be elimination, which is the reverse of addition to pi bond. And you'll see when I draw the mechanism below. So that is my compound. And here I'm going to form a pi bond and break a sigma bond. So I end up with a radical chlorine atom and then a new pi bond. And last common pattern mechanism you'll see in radical reactions is coupling. And this is an example of one where you start with two reactants that each have a radical and you end with a product that does not have a radical. So those are my two compounds. Draw the fishhooks to empty space here to form a new sigma bond. And that is my product, right? It looks similar to if someone texts and they do like the shrug, right? That's what this compound looks similar to. I thought it'd be fun to put one in here that had a little bit of a common appearance you'd see in everyday life. All right, so these are the common patterns you'll see in radical mechanisms. So really, no matter what radical reaction's going on, they're generally going to follow one of these patterns. So it's super important to recognize that each of these types of reactions can happen. So when you're given unknown molecules, or you're given molecules but you don't know what type of reaction is going to undergo, or maybe you don't know what the product is and you have to determine that, having these 6 patterns in mind can be very helpful. All right, I'll see you soon in the next video with radicals.